Good afternoon, everybody. Let's get started. For announcements, so see Canvas for the upcoming assignments. Homework 2 is due this Friday, and Lab 1 will be due this Friday. You'll perform Lab 2 on Friday, and then Lab 1 is due. So that's coming up. Okay, so last class, we talked about capacitors at the end of the lecture. We talked about capacitors and removing noise from power and sensor signals and other voltages using decoupling capacitors. And we also started talking about inductors. So I wanted to continue the review. We're going to finish up, I think, all of that review material today. We're going to move on to maybe test equipment today, probably next time. And we'll continue on there. Okay, so we talked about inductors, and I showed you different kinds of inductors. And I wanted to point out again that inductor impedance, the magnitude of the impedance, increases with frequency. And we saw that the capacitor impedance reduces with frequency. So they act in an opposite way with frequency. And so I wanted to talk about some applications of inductors that clarify what they do. Instead of just saying they're an energy storage element that's reactive, let's talk about what they do. So inductors are commonly used in electrical filters. So electrical filters select signals within a specified passband, and they block signals and noise in other frequency bands. So here is a simple but effective RF filter that works at 28 megahertz. You can see the inductors here. These inductors are just coils of wire. I forget what inductance they are, but they're coils of wire, and you can see kind of goop on them. That's just hot glue to hold them in place, because the way you can tune inductors or vary their inductance, especially when you have an air core coil like this, is you can spread the coils out, and you can push them together to increase and decrease the inductance, and you can tune your filter that way. So you see a couple capacitors, these two big inductors, not really big, and a couple capacitors here. So we'll talk about that filter in a little bit, or the filtering characteristic in a little bit. You can also create oscillators. So oscillators create usually sinusoids. And so you can use inductors and capacitors to essentially, again, create a filter so that you get a feedback loop. Just like when you hold a microphone in front of a speaker and you get feedback, well, you can tune that frequency of feedback so you can get a precise frequency using inductors and capacitors. You can use inductors in DC to DC converters. We're going to work on those. We're going to talk about those. You'll see how inductors store energy, and you can boost voltages, you can reduce voltages from one DC value to another. Okay, and you're going to work with this board in lab. This is a DC to DC converter, and here's the inductor right here. But each of these applications is based on the I versus V characteristic, V equals L di dt for an inductor. And again, thinking in terms of phasors and impedance, the impedance of an inductor is J omega L. The magnitude of inductance is, or the magnitude of impedance for an inductor is omega L. All right, so let's take a look at an example using an inductor, and this is an electrical filter. So here's a filter. I just have an inductor and a capacitor. So we can build this simple circuit just using one inductor, one capacitor, and create a bandpass filter. And what bandpass filters do is they pass frequencies in a certain band around a center frequency. That's called a pass band, and they reject signals outside of that pass band. If you plot the frequency response, so remember these from the Intro to Circuits class, if you took it with me, here's the magnitude of H of F. H of F is the ratio of phasor voltage output divided by phasor voltage input, right? Take the magnitude. We're plotting the magnitude here. And so here's that response. So you can see that this filter, let me talk about these axes. This is h of f, shown from 0 to 1. Here's frequency along the horizontal axis. And so there's this band right around 5 kilohertz that is passed. So that means right here at 5 kilohertz, we have a 1. That means if you have an input of 1 volt peak to peak, you have an output of 1 volt peak to peak. And as you move away in frequency from that center frequency, from that 5 kilohertz center frequency, any signal away from that center frequency gets rejected. So signals with frequencies above and below 5 kilohertz in this passband are rejected. Okay, so that's great. You can kind of see this. You could think about building filters like this. I want to talk about intuitively why this works, just to point out that you could sort of figure this out on your own, because, well, let's look at this inductor and this capacitor. This inductance and this capacitance, at some frequency, you're going to have a positive reactance, right, or a positive imaginary impedance, and the capacitor gives you a negative imaginary impedance. And at some frequency, those impedances cancel out, right? So you're going to, if you had like, I don't know, plus J 10 ohms and minus J 10 ohms, and they cancel out and you get 0 ohms, at some frequency, this filter looks like it's a wire with a little bit of loss practically, but it looks like those impedances cancel out, and it looks like this source is connected directly to this load. So the source is a realistic source. We'll talk about Thévenin, but you probably remember that. This is a realistic source with a 50 ohm output impedance. Here's a 50 ohm resistance load. So at the center frequency, this filter looks like a wire, and you're connecting the source directly to the load because the impedances cancel out. As you increase in frequency, you know that the inductance, the inductive impedance increases. So that magnitude increases. And so that gets big. So it's like adding essentially a big complex resistor here. And that's going to cause less of a voltage across the load. So that's as you increase in frequency, you would get a lower voltage across the load. As you decrease in frequency, the magnitude of the impedance of the capacitor increases, right? And so that's going to reduce the voltage across the load. Okay, so that's why you get this characteristic. If you deviate from that resonant frequency, one of those components, the inductor or the capacitor, is going to start essentially blocking current or acting like a high impedance. All right, and there are more complex filters, of course, you could build. So this kind of structure, this LC structure, can be used in multiple sections to build more capable filters. So what's more capable mean? It means you can have defined passband bandwidth. Right? You might have a 1% or a 10% or a 5% bandwidth filter where it looks pretty flat, like this one here. Here's a frequency response of a filter. See frequency on the horizontal axis, frequency response, h of f on the vertical axis. And so you could have a flat passband, and then you could have steep roll-off, okay? And so you can control those different characteristics of the filter using these L's and C's. And there are filter design tools that you can use for different types of filters: Chebyshev filters, elliptical filters, Butterworth filters, different types of filters. And then you can go simulate them. So if you ever want to build a filter to pass a signal, let's say from a sensor or an audio source, and you want to block noise outside of that band, you can design filters online, and then you can use tools like LT-Spice. LT-Spice is a SPICE tool. It's a circuit simulation tool. We're not going to use it, but I want to point it out. It's very useful, and it's free. It's been around I've been using it for 30 years now, at least. And it's very useful for getting frequency responses, plotting frequency responses like this. Okay, so there's an inductor example. That's why we have to know inductors and capacitors. All right, so let's do a clicker problem. I want to talk about power delivered to an inductor. This also this also could describe power delivered to a capacitor. It's the same lesson, but power can't be delivered to an ideal inductor. I'm going to show you why. So here, find the average power delivered to an inductor from a sinusoidal source. So you take this current source and you set it up in lab, and 10 sine 10 to the 6t, and you connect that directly to an inductor of 0.3 microhenries. And so you have a current flowing through that inductor, you have a voltage across that inductor. The voltage is L di dt. We can calculate that. L is 0.3 microhenries. I is 10 sine 10 to the 6t, so you get this. So V of t is 3 volts peak to peak, cosine 10 to the 6th radians per second t. Okay, so now you're going to find the average power. I'm going to walk you through this a little bit. The instantaneous power at any given time, and this is the power that is delivered to that inductor, P is equal to IV. I and V vary with time, so P varies with time. If you want average power, then you have to integrate over a cycle of power. So the average power is 1 over the period, the integral over that period of P of t. So looking at a couple plots here, here's the current through the inductor. Right? That's just a plot of 10 sine 10 to the 6t. Right? There's the current. We calculated the voltage. Here's the voltage across the inductor. Right? Another sine wave, as you would expect. You have 3 cos. 3 cos 10 to the 6t. Same frequency as the current. A different amplitude, but also notice a different phase here. Notice that I have a 0 crossing here of current at time 0, and I have a peak here at time 0. So when you multiply current times voltage, you get this. Here's the instantaneous power for that inductor, right? So notice that you have positive power, negative power, positive power, negative power. We're using the passive reference configuration that we talked about in the Intro to Circuits class. Okay, so let's start the clicker here. Answer this question: what's the average power delivered to that inductor? Just looking at that plot of instantaneous power. And you can even mentally integrate over a cycle. All right, take another 10 seconds. Take a guess if you haven't answered already. Remember, if you just answer one question during a session, you get credit for that clicker session, and you don't even have to get it right. You have to answer during half of the clicker sessions. That's hard to say, to get full credit for the clicker credit. Okay, so let's stop here. So notice how when power is positive, you have power into the inductor. Right? You're storing energy in that inductor. And when you have a negative half cycle of instantaneous power, power is being supplied by that inductor. It's coming out. And so half the time power is going in, half the time power is coming out. And so on average, you get 0 watts delivered to the inductor. But notice current is flowing, right? Current is flowing through this wire back and forth, right? But there's no average power delivered to that inductor. And this is why we're not going to talk a whole lot about it, but this is why when you have loads connected to a power system, like an AC power system, that are inductive or even capacitive, that the power flows from the source to the load, from the load to the source, and you get this exchange of energy back and forth flowing through, let's say, a non-ideal wire that has resistance. So you're heating up that wire, you have current flowing through it, but you're not actually delivering any power to the load. That's bad, especially for the power company that wants to charge you for the power you use. So there's loss that can happen in the transmission lines when you have an inductive or a capacitive load. And so what you really want is you want the load to look like a resistive load so that you can deliver time average power to it. Okay, so continuing on with a quick review of concepts we're going to use. So remember Kirchhoff's current law. If I define currents into or out of this node, a node is a connection among circuit elements. Kirchhoff's current law can be expressed in three ways. You can sum the currents entering the node, set that equal to 0, right? And if you have currents leaving a node, you can turn that arrow of the reference direction around and write a minus sign. So I2 becomes minus I2 entering. So here we have I4 leaving, but minus I4 entering. So the sum of currents entering a node is 0, right? I1 plus a negative I2 plus I3 plus a negative I4. Right? You can sum the currents leaving a node, set that sum equal to 0. So leaving that node, minus I1 plus I2 minus I3 plus I4. Right? It's the same equation. Just multiply both sides of the top one by -1, or the sum of currents entering a node equals the sum of currents leaving a node. Okay, so using the original variables without the minus sign, I1 plus I3 equals I2 plus I4. Right? If you have any question about that, stop by office hours. If you want to see a longer explanation, click on the KCL review video on Canvas. Kirchhoff's voltage law applies to loops and voltages that I've defined. So here are voltages I've defined on a circuit that I've made up. So KVL can, as KVL says, the sum of voltages around a loop is 0. So if I define a loop, for example, loop 1, I can start anywhere on that loop. I can go either direction. I've just chosen to start at the lower left here. When I write a KVL equation, when I hit a minus sign, I write a minus sign. When I hit a plus sign, I write a plus sign. So this equation is minus VA plus VB minus VC equals 0. Okay, here's loop 2. Here's another loop. So I can write that equation minus, or no, I hit a plus VD minus VC minus Vx equals 0. Back to the starting point, always write equals 0. Notice that I have voltages defined across circuit elements, but I also have a voltage defined across two terminals where there is no current flowing into or out of those terminals. That's just fine. You can have a voltage across two terminals between which nothing is connected. Right? So that's that KVL. And you can use outer loops. You don't have to just stick to inner loops. So in this case, minus VD plus Vx minus VA plus VB equals 0. And again, I use the approach, when I hit a plus, I write a plus. When I hit a minus, I write a minus, and that keeps things nicely. And when I say plus and minus, I'm referring to the polarities of those voltages as written, those reference polarities. Okay. And I'm going to show you in a minute, like that, this is basic review, but I'm going to apply this to show you a problem that can happen with an electrical circuit, and this is usually dealt with by mechanical engineers. But before we get there, let's talk about voltage and current division. A quick review. Voltage division describes how voltage splits up or divides among series resistors. So if I were given a voltage Vs across 3 series resistors, V1 is the voltage across those series resistors times the ratio of. On top goes the resistance across which you want to find the voltage. On the bottom go the sum of the series resistances. Likewise for V2, likewise for V3. Okay, so why is this useful practically? Well, you're going to use a potentiometer in lab on the DC to DC converter. Often these potentiometers are used to create some kind of adjustable voltage reference, right, for a comparator or for some other purpose. And sometimes, well, I'll leave that for later, but you can see here, you can use this circuit to create a variable voltage between 0 volts and 12 volts using this potentiometer configured as a voltage divider. Current division describes how current splits up among parallel resistors. So if I have 3 parallel resistors, I have current coming into this parallel set, and I want to know what is I1. Well, I1 is the current coming into that parallel set times this ratio. On top, in the numerator, is the reciprocal of the resistance through which we're trying to find the current. In the denominator is the sum of reciprocals. Likewise for I2, likewise for I3. Okay, so if any of this, if you want a refresher on any of this, take a look at those videos on Canvas, and you can just click right on current division or voltage division and see a review. Okay, so now let's look at a practical application, maybe some insight using Kirchhoff's voltage law and voltage division. And so this is an example which illustrates the importance of connector pin engagement and the order of pin engagement and power sequencing. So it's often, in a couple places I've worked, that mechanical engineers choose connectors for electrical interfaces, like these micro D connectors or these industrial circular connectors. Right? A mechanical engineer might choose those based on environmentals, shock, vibe, temperature, maybe even thermal expansion. So mechanical engineers are typically the ones working with an electrical engineer that choose the interface connectors. Let's suppose we have a simple power supply circuit. Looks like this. It's just 2 voltage sources. So you might have 2 batteries here, or 2 voltages out of a power supply unit. And I have a connector that has 3 conductors. And I'm connecting that to another sub-circuit, this load, that I'm modeling as 2 resistors. So that's the load circuit. So what you really want, you really want 5 volts across this load R1, and you want 24 volts across this load R2. That's the intent of connecting this power supply to this load circuit. Okay, well, let's suppose that this load R1 is some kind of maybe digital circuit, and it has a voltage range outside of which you would damage that circuit. Okay, so let's say -1 volt to 6 volts are the absolute maximum limits of that load. Right, so you think, well, so what? We have 5 volts and 24 volts. I'm going to get 5 volts across R1. I plug the connectors together. I'm going to have 5 volts across R1. But let's suppose that, in real life, there is no simultaneity of mechanical connections. So these pins do not engage simultaneously. So the question is, what is V1 if the ground connection, this bottom connection, engages last? So you're just putting this 3-pin connector together. The 5 volt connects, the 24 volt connects, but ground connects last. And eventually, when you plug the connector together, ground connects, but for a little small instant in time, that ground connection is not made. What happens? So what we can do is let's figure out what this, I'll call it VS value here is. It's the voltage between these two top nodes here. We can figure VS out using Kirchhoff's voltage law. -5 plus VS plus 24 equals 0. I get VS is minus 19 volts. So if in this condition, in this state where I have two connections made, the third not made, I have 19 volts here. Okay. And so this is the case, right? Minus 19 volts, it has that polarity. The ground connection is not connected. And let's suppose these loads are modeled as those two resistance values, 1K ohm resistors. By voltage division, we can figure out what is V1. Well, V1 is VS times R1 over R1 plus R2. So it's the voltage across those two series resistors, right? Those resistors are in series in this configuration. The same current flows through them. And so for series resistors, you can apply voltage division. And the voltage across R1 is the voltage across the series pair of resistors, times the ratio of the resistance across which we want to find the voltage divided by the sum of the resistances. So you calculate that, and you get minus 9.5 volts. Right? So that's not good because we're outside of these limits for resistor R1. So just because that pin connected last for a small instant in time, for a small duration in time, we applied minus 9.5 volts and blew out that component. Okay, so connector engagement order isn't always important. In this case, this is an example where it is important. And so if a mechanical engineer is choosing the connectors, there's a conversation to be had with the electronics designer. Does order matter? Right? And there are at least a couple approaches, mechanical approaches and electronic sequencing that you could use. For example, you might have the ground pin engage first with some kind of connector that has a longer pin, and the power supply connections engage later. Or you might disable the power supplies using transistors or otherwise some other electronically controlled switch. So until certain connections are made, you don't allow the power supplies to be enabled. Okay, but that's something that, again, I've run into with mechanical engineers in plugging wire harnesses together, and we had to figure out what's the best way to not blow out the load. Okay, any questions on that? All right, nothing seen, nothing heard. Okay, so this is an example of, what's the big deal with voltage division in KVL? Here's an application where you can determine if there are any damage risks to a circuit. Let's talk about Thévenin equivalent circuits. So Thévenin equivalent circuits are a model of an actual circuit. So if you have any linear circuit with resistors and sources, dependent or independent sources, right? Independent sources are not controlled by any other voltage or current in the circuit. Dependent sources do depend on voltages or currents elsewhere in the circuit, like an amplifier is a dependent source. So any linear circuit with resistors and sources can be modeled as a Thévenin equivalent like this, with just simply a voltage source and a resistor. Right, so VT is the Thévenin voltage. RT is the Thévenin resistance. Now, you don't often outside of circuits class use the name Thévenin. At least in my experience where I've worked. The Thévenin voltage, as you might recall, is the open circuit voltage of the circuit. People will talk about open circuit voltages. And Thévenin resistance is more often called output impedance, right? Not just resistance, but impedance. Usually that output impedance is real. No, often it is. Often it's real. So the output impedance is actually an output resistance. So if you hear someone talk about the output impedance of a function generator, the output impedance of a function generator is usually 50 ohms real. But you won't often hear, what's the Thévenin resistance of a function generator? Okay, so common applications of Thévenin equivalence. You can model a complicated circuit with a simple circuit like this to understand or convey or specify the output interface without giving the details of what's happening within the electronics box. You can also determine the load resistance that results in maximum power transfer from a source to a load. Okay. So, so this can be any linear circuit with resistors or sources, or it can be a more complicated circuit that has transistors and diodes and MOSFETs, things like that. But the circuit just has to behave linearly, like it's a circuit with resistors and sources and modeled by dependent and independent sources. So communications equipment, communications transmitters can be modeled with a Thévenin equivalent. Audio equipment that acts as a signal source can be modeled as a Thévenin equivalent, and test equipment, the output of a signal generator, can be modeled with a Thévenin equivalent. Okay. And so what you're going to see is that if for example you have test equipment or audio equipment, you have this audio microphone and you want to deliver the most power possible from that microphone to an amplifier or to some other circuit, maybe it's a sound detection circuit, then you want to know, how do you maximize power transfer from that source, from that audio equipment to the load, to either an amplifier or maybe some other detection circuit. And that's where modeling that equipment as a Thévenin equivalent with a Thévenin resistance or output impedance is useful. Okay, so so let's talk about an example, a Thévenin equivalent example. So let's suppose you have a circuit that has an output. It has two terminals, A and B. It's some kind of realistic source. Okay, and you want to find the maximum power transfer between source and load. Well, that maximum power transfer happens when the load resistance equals the Thévenin resistance, right? And then we need to calculate RT, or we need RT to calculate VL, right? So, for example, a function generator generates AC waveforms, square waves, sine waves, and you'll notice that you'll see 50 ohms written next to these connectors. So you go to lab, look right next to the connector, it'll probably say 50 ohms. That 50 ohms is the output impedance or the Thévenin resistance of this function generator. Okay. A spectrum analyzer with a tracking generator. Here's an output specified with 50 ohms. So that's what that 50 ohms means right there. Incidentally, this spectrum analyzer has an input, and it's specified with an input of 50 ohms. So that's the load. So that would be the load, since this is an input to a piece of equipment. Here's another RF signal source. This RF signal generator shows output 50 ohms. Okay, again, 50 ohms is common for RF equipment, RF circuits, except for television. Anything related to TV in your house is 75 ohms, not 50 ohms. Here is an RF amplifier. You can see there's an RF input and an RF output, 50 ohms, 50 ohms. So 50 ohms is common for RF circuits. It's common for signal generators and test equipment that deals with AC signals, right? So some other equipment, like audio equipment, speakers, audio amplifiers, have different output impedances. All right. And so one takeaway that I want you to have from this is you see these signal sources, this function generator that you have in lab, for example, and you think, oh, I'm going to set 1 volt peak to peak, and no matter what I connect to that signal source, that function generator, I'm going to get 1 volt peak to peak. Well, that's not true, because 1 volt peak to peak actually sets, depending upon the impedance setting of the function generator, it sets what this VT is going to be in terms of the sinusoidal amplitude. But you have this resistance here. So the voltage at the terminals of that test equipment is going to change depending upon what load you apply. Okay. So that's an important takeaway for test equipment. We'll talk about that. Okay, here's a little more complex example. Let's suppose you're using a device, an analog to digital converter, to sample a high frequency signal, an RF signal. So an ADC, an analog to digital converter, periodically samples an analog voltage and then converts those samples into digital values that are proportional to the input voltage. Now, ADCs have a full scale range. They have a full scale voltage, outside of this range, the signal becomes distorted because you've hit the maximum of the digital values, either the maximum or the minimum. Okay, so here's an ADC chip right here. Okay, so here is an example. Here's an antenna. The antenna receives radio frequency signals. I have some RF electronics. Those RF electronics might amplify the signal and filter the signal. But at the output, you get a voltage. You get a voltage versus time that you can expect it's going to be a sinusoid, maybe a modulated sinusoid. Okay, and that ADC circuit, let's say it has a 50 ohm input impedance, real, 50 ohm real, looks like a resistor. And let's define the average power here, right at the input of the ADC. So you can model this antenna and these electronics. You can model those with a Thévenin equivalent, right? It's a linear circuit, and it behaves as if it was created using ideal voltage sources, dependent, independent, and resistors. Okay, so this is the antenna and electronics model. The ADC circuit can be modeled just as a resistor. It has a 50 ohm input impedance within a certain range of frequencies. So I've defined a voltage here, the Thévenin voltage, an amplitude times cos omega t, and here's the load voltage, A sub L, this amplitude, cos omega t, same frequency, different amplitude. Okay, so this practical example is, suppose you're trying to determine the maximum power that can be received by an RF communications receiver. So you have this RF section and you have this ADC section. What's the maximum power that can be received successfully by this receiver without distortion? So let's say that ADC circuit has a full scale range of 1 volt peak to peak. So what is the maximum power that can be applied at the input to the ADC from the antenna and RF electronics? So you've got an output of the RF electronics here. How high can that power be without distorting the signal? That means without exceeding this 1 volt peak to peak range. So as I mentioned, RF sources, all RF equipment except for television related, has input impedances of 50 ohms. So that's the Thévenin resistance. RF loads typically have input impedances of 50 ohms. All right, so let's convert that 1 volt peak to peak to an RMS voltage for this power calculation. We're trying to figure out how much power average can be delivered to this ADC circuit. Okay, so the V sub L, right, where is that? That's the load voltage peak is the peak to peak voltage divided by 2. So the amplitude A sub L is 0.5 volts. Okay, because I have a 1 volt peak to peak maximum voltage, so it's going to be a half volt peak voltage. The RMS value is what we use to calculate power. We need that. So that is the amplitude or peak value divided by √2 for a sinusoid. And we get 0.3536 volts. Okay, so we use that RMS voltage and the load resistance to calculate power. Remember, you can only deliver power time average to a resistance. In this case, we have a real value. We have a resistance value here. It's not inductive. It's not capacitive. And so P sub L, the power delivered to the load, is the RMS voltage across the load squared divided by R, and we get 2.5 milliwatts here. All right. What is this showing? This is showing that, well, first, you can calculate power delivered to a load when you have the Thévenin equivalent circuit and the load resistance. It shows that you can determine things like what's the maximum signal voltage that I can have across these terminals A and B, and what's the maximum power I can deliver to the ADC circuit, or what's the max power that can come out of the electronics section, right? That determines the range of field strength of RF signals you could receive. Okay, and it also shows, well, what if I don't have an R sub L equal to R sub T, right? What if this were an ADC with 100 ohm input impedance, right? You could figure out, well, how much power would be delivered to that ADC, and then what would the effect on the voltages be at the input? Okay, so there's an example case here. If you're speaking with an RF electronics engineer, they're going to speak in units of dBm. And we'll talk about that later, why we do that. But 2.5 milliwatts is 4 dBm. So dBm is 10 log base 10 of power expressed in milliwatts. All right. And we're going to get to, so we're going to use this later when we talk about RF topics in the class. So you'll have this slide. These slides are posted on Canvas. And if you have to come back and calculate powers for a load for an RF circuit, remember this slide. Okay, so this is the end of the circuits and electronics review. We're going to talk about test equipment next, but I want to give you some takeaways. So there are some practical benefits of having a good feel for the basic circuit theory, even across disciplines. Even if you're not an electrical engineer, having this basic circuit theory of voltage division and understand how voltage is going to be divided, it's really useful to create better designs and to do less rework on designs maybe that don't work as you expect. Kind of like that, connector engagement problem. You don't want to have to go redo all that work and choose different part numbers all because of connector engagement problems. And there are some practical cross-discipline knowledge topics that help identify potential problems before they become problems. So it's good for a mechanical engineer to work with an electrical engineer and have some knowledge of electrical engineering so you can help point out problems that maybe you see could happen. And understanding of practical circuits really does help create more effective designs. It helps hold more effective system level meetings when you have different engineering disciplines in the room. and it helps with design reviews so that mechanical engineers have some electrical knowledge, electrical engineers have some mechanical knowledge, and you can get together you can put together a better circuit, a better product, or a better system. Okay, any questions on any of that review before we move on to test equipment? All right. All right, let's start the discussion in the few minutes that we have left on electrical test and measurement. And so I'm going to give you an overview of some equipment I think you've used before, but it helps to have a little bit of deeper knowledge as you get into projects and measurements that are as complex, not that complex, as the project circuits that we're getting into. Okay, so let's talk about electrical test and measurement for electronic system prototyping. So when I design systems, I take a lot of measurements because usually it's starting with basic components and building up into subsystems and building up into a system. And the test data at every level is really important, especially when things stop working. You want to go back and be able to check lower level measurements in lower level subsystems to be able to see what happened, why the system stopped working. Okay, so test data is important through the incremental and iterative process of creating an electronics prototype. So I'm going to focus on prototype development here. These are generally the stages of prototype development. You have some kind of concept in mind, and you document that concept. You write down what you want your product or your circuit or your system to do. From that, you develop a detailed design, and you might, in prototype development, actually build some of those sub-circuits to make sure they work before you go commit to putting them into a final circuit board. So there's detailed design, then there's typically incremental build for an early prototype. And then once you get enough of the system together, you can start requirements verification. Right? And then once you have your prototype and it works in a certain way, you might say, okay, how do we improve this product or this circuit? And then you might revise your detailed design and start all over again in a spiral. So we use test equipment in concept development to emulate key functions. Okay, so for example, you're going to be working on your project in lab that is going to involve pulse width modulation from a microcontroller. Well, long before you get your microcontroller programmed and built and set up, you can use test equipment to test pulse width modulation using a function generator. So here's the function generator. It can easily create a PWM signal with a specified high voltage value, low voltage value, frequency and duty cycle. Okay. So then you can move into detailed design and you can verify key functions of subcircuits. So for example, you can take what is going to be your RPM sensor, you can take your infrared emitter and detector, forming a proximity detector, and you can test it, right? You can check, well, does this really do what I need it to do? Can this be sensed by the microcontroller before I even have the microcontroller? You might have a motor with a spinning propeller and you want to see, will this work? Will this circuit board actually detect blade crossings? And how do you know if it's detecting blade crossings? Well, you can view the output on an oscilloscope, and you can check. Okay, I'm not getting erratic behavior. I'm getting regular behavior. I can measure the frequency of the output of the infrared sensor. I can convert that to RPM, and so yeah, this looks like it will work as an RPM sensor. Okay, and then Okay, so concept development, detail design, and I'm hitting the wall on time, so we'll continue this next time, but we'll talk about using test equipment during the build, requirements verification, and improvement phases. But for now, see, I think I stopped here. But for now, in closing, see Canvas for the upcoming assignments. Let's see here. Sorry, my video went away here. So see Canvas for the upcoming assignments. You have Lab 2 this week. You will be performing. Lab 1 is due this week, and Homework 2 is due this Friday. If you haven't checked them out yet, see the ITLL workshops for any skills you may want to strengthen. Those are linked to the Canvas site. Check out, let's see, what else here? Check out the homework that's due. I already said that. Oh, check out the videos. I posted review videos on Canvas. So if any of these concepts need strengthening that you feel, check out those videos. You can watch about 5 minutes and strengthen those. So I will start office hours in just a few seconds. So just stay up on the Zoom call if you would like to chat. If not, I'll see you next time. Have a great night.